In today's lesson, we're going to continue looking at hypothesis tests when we have two samples worth of data. Now, at the end of the last lesson, I said that we were going to look at what happens if the data are not independent in this lesson. That's not quite true. That's what we're going to be looking at in the next lesson. In today's lesson, what we want to look at is what happens if we don't have a normal population, or if we don't have a large enough sample size to use the normal approximations. So specifically, we're going to be considering t-tests and confidence intervals. And again, anytime we're thinking about a t-test, we're thinking about the t-distribution coming out. So we have two primary objectives for today's lesson. We first want to construct hypothesis tests or confidence intervals when we're dealing with small sample sizes and unknown variances, right? So that's sort of been the differentiating point that we've been making throughout all of our hypothesis testing. We also want to look at what is called the pooled variance estimator if we're able to assume that we have equal variances, right? So to motivate the lesson today, I want to bring up this picture of an atom, right? And this is sort of the Bohr model of the atom. I'm sure we all saw it in our early science classes, right? And one of the things that you end up learning if you continue studying chemistry is that this picture of the atom is entirely incorrect, right? It doesn't resemble anything like this in the real world. But we get taught it this way when we're first being introduced to these concepts because it provides us with some useful intuition about how these different processes work, right? And for most people going about our lives day to day, if you think about an atom in this way, you're not going to end up sort of being misled too much. If you wanted to continue into chemistry, you need to understand sort of deeper nuance of different models. And I think that this is sort of an important parallel that happens in a lot of subjects, right? Where what you start to learn is not necessarily the end point of everything. And it's sort of a useful foundation that you could build upon if you want to continue that knowledge going forward. And I think that it's particularly important to think about this with respect to hypothesis testing. Right, so what we've been talking about this whole time is normally we're testing means, right? We looked at proportions as well. And we've basically said the sampling distribution is always either going to be normally distributed or a t-distribution. If we have a big enough sample, we can just approximate that t-distribution with a normal distribution anyways, right? And this is going to be approximately true in a lot of situations, and it's going to be exactly true in some situations that we might care about. Ultimately, this is not the end of hypothesis testing. In fact, this is hardly even the beginning of hypothesis testing. If you wanted to go on and do sort of more advanced statistics, you're going to think a lot more deeply about these types of ideas. However, these are procedures that you can actually use, and they're actually going to be effective in a number of scenarios. And if you're dealing with sort of data in the way that many people are going to interact with data in their day-to-day lives or in their work, these are going to be sort of acceptable. I guess I only want to emphasize that we've been seeing the same distributions come up over and over again, the same procedures come up over and over again, and it's a really effective way of getting through with the types of assumptions we're making. But just keep in mind that this is not actually where these concepts end. And if you want to start applying these in the real world in a way that's sort of statistically rigorous, you're going to have to continue with these ideas. And this will be the right foundation for it. It'll give you sort of the building blocks you need to work with, but that it does go deeper than what we're looking at in this course. So previously, we assumed that the variances were known or that the sample sizes were large enough that we could use normal approximations to the sampling distribution. What if we want to conduct population when we do not know the variances and also the sample sizes are quite small, right? We'll still look at the same estimator that we've been used to looking at, right? Where we take, in this case, we're thinking about the difference between x bar and y bar, testing it against mu1 minus mu2, and we can scale that by its standard deviation, or the estimated standard deviation. This is going to approximately follow a t-distribution, just like we would have assumed in the single sample case. However, it's going to be a t-distribution with a very strange number of degrees of freedom. Okay, and so to compute the number of degrees of freedom, we basically are looking at the variance of our estimator, and then we divide that by these terms that sort of scale the variance by some different quantities here, right? Ultimately, what you can just do is take the smaller of n minus 1 and m minus 1, right? And that'll be conservative in this case, okay? So we can take the t-distribution with n minus 1 or m minus 1, whichever is smaller, just like we did in the single sample case, all right? So once we form the test statistic, we can use critical values from the t-distribution, just as we did before. We can compute p-values, just as we did before. Other than changing out that distribution and thinking about the degrees of freedom slightly differently, we can apply the exact same procedure that we're used to looking at with our t-distribution there. So you can test the two-sided hypothesis, mu1 minus mu2 equals delta naught, versus a one-sided or two-sided alternative, tested in exactly the same way that we're getting used to, right? So you look at the tail probabilities, which tails provide evidence against the null hypothesis. Those are the tails we have to add up in terms of forming our p-value. This will apply anytime that we have a sample of at least 2, right? So the important point to make here is that the t approximation, again, or the normal approximation to the t, will hold with large enough samples, but of course you can always rely on this t-distribution. So to get the t-distribution, you just need the sampling distribution to be approximately normal, which will happen if the populations are normal, or if they're non-normal, but you have a big enough sample size, right? So again, this doesn't help for small sample non-normal populations, but it helps with small sample normal populations where you don't know the variances, and this can be used in non-normal populations as well, but you need more observations for that. The procedure we previously saw when we used normal approximation applies only if the variances are known or if m and n are both large enough, right? So we can apply the t-test whenever we want to under those normality assumptions. We need known variances or large m and n to apply the normal approximation. Now, oftentimes, it's going to be reasonable to assume that the variances of the two populations are going to be equal, right? Often we're going to be thinking about intervening in such a way that might shift the mean, but isn't likely to change how spread out this is. And if we have a reason to assume that the variances are going to be equal to one another, then what we can do is actually use all of the data to estimate a common variance. We call this common variance estimator the pooled variance estimator, as in we're pooling all of our data together. And there's sort of a particular way that we go about forming this. So if we were to think about the variance of x bar minus y bar, if you assume that sigma 1 equals sigma 2, then you can just factor out sigma 1 and sigma 2, and we get a overall variance of sigma squared times by 1 over n plus 1 over m. Now, what we can do is use an estimator for the pooled variance to get this sort of weighted average here, right? So you take n minus 1, you multiply it by the variance of x, m minus 1 times the variance of y, and then divide by n plus m minus 2, right? And so what this gives us is sort of a weighted average between our two different variances, and this will give a good estimate for sigma squared. We can then get the estimator being scaled by, in this case, it should be our standard deviation. So it would be SP times by the square root of 1 over n plus 1 over m. So I'll fix that typo in the slides there. But the idea is that SP squared should be approximately the same as sigma squared. And so then the variance is going to be SP squared 1 over n plus 1 over m. So that's the variance. And so the standard deviation is going to be the square root of that quantity. This is going to have a t-distribution if we scale by this standard deviation here with m plus n minus 2 degrees of freedom. And so if you remember with our t-distribution, the more degrees of freedom, the closer to normality it would be. And so one of the benefits to doing this, if we can make this assumption in a reasonable way, is that we get more degrees of freedom, right? So if you're thinking about having to estimate both variances, we're going to have the smaller of m-1 or n-1. If you get to pool everything together, then we get to have m plus n minus 2, which is going to be larger, which is going to be a t-distribution which is closer to the normal distribution, right? So we get some sort of benefit from that. Now, in order to make the assumption of a pooled variance estimator, there has to be a good subject matter reason to believe that the variances are equal, right? So there would have to be some underlying justification for why these two groups should have equal variances. Now, sometimes you're going to see advice that says that you can test this from your data, right? And so as a general rule of thumb, what some people will say is that if you consider the ratio of S1 squared divided by S2 squared, then if this ratio falls between 0.5 and 2, then the pooled estimator may be appropriate. So in particular, what this is saying is that if 0.5 is less than or equal to S1 squared divided by S2 squared, which is less than or equal to 2, then you can make the pooled variance estimator. Now, I'm going to advise against this as a general rule of thumb. This will work in certain cases, and it's not bad. But generally speaking, if you don't think that they're going to be a common variance based on the subject that you're actually studying, then I don't think you should use a pooled estimator, right? It's sort of a less conservative estimator, and the non-pooled estimators that we looked at are actually always valid, right? Even if it turned out that they were the exact same, those are still valid and they provide a more conservative test, right? And so doing this, you'd have to have a really good reason why they should be, rather than relying on this to be driven from your data. Now, if you actually observe something that was outside of this range, even if you had a good reason to believe it, I would still not use the pooled estimator, right? And so I would say you sort of need both of those to be true if you're following, I think, best practice. Now, if there's no good reason to use the pooled estimator, don't use it. Again, all you're going to be doing is sort of inflating your confidence, and it's not going to be a justified inflation of your confidence, right? And so then being more cautious is always advisable in these situations. And so if you don't have a justification for it, just don't use it. Look towards other possibilities instead. So, in summary, if our sample sizes are small and we don't know our variances, we're going to rely on the t-distribution instead. The number of degrees of freedom follows sort of a strange formula, but we can just think about it as being the lesser n-1 and m-1. If there's a good reason to believe that the variances are going to be shared between your two independent populations, then you can estimate using the pooled variance estimator instead. Okay. In the next lesson, we're actually this time going to look at what happens if we don't assume that the two populations are going to be independent of one another, at least in one sort of specific way. And so I look forward to seeing you all in that lesson.